So, last time we have discussed the various tests for the convergence of the series. Now, in continuation we will do few more tests, discuss few more tests like a comparison test and limit comparison test, and after that we will come to the conditional and absolute convergence of the series. So, first test which in continuation we have another test which is known as the comparison test. Comparison test. The test says let x, which is say x n, and y, say y n, be real sequences and suppose suppose that for some k which is of course a positive integer, we have this inequality 0 is less than equal to x n, less than equal to y n, and this is valid for n greater than equal to k. It may be true for all n's also. If not possible, then at least after certain stage, if this inequality holds, or then the series, the convergence of the series, then the convergence of the series sigma by n is of course 1 to infinity. Convergence of the series implies the convergence of the series sigma x n 1 to infinity, 1 to infinity, 1 to infinity, and the divergence of the series of the series sigma x n is 1 to infinity implies the divergence of the series sigma y n. In fact, this type of result we have discussed already in case of the sequences. So, similar results we have for a sequence of non-negative series, we have sequence of the non-negative terms, all terms are non-negative. So, what the comparison test says, if we are having a series say sigma n of each terms is non-negative, then to discuss the convergence of the series or to find out the nature of this series sigma x n, if we are able to identify some sequence by n for which this relation 0 is less than equal to x n, less than equal to y n holds for either for all n or maybe after certain stage, then the convergence of this by n will imply the convergence of the series sigma x n. It means that with the help of x n, if we find out a suitable y n for which the convergence of the series sigma y n nature is known, then one can easily establish the convergence of y n. And in case if this relation is true, but if the series is diverging sigma x n, then the divergence of y n will be there. It means, if we are interested to know the we expect or something that the series is diverging, then we have to find this relation where this is diverging, then this will diverge. So, this is the main motto for this comparison test. The proof of course is very straightforward. Suppose we have this series converges, given suppose the relation hold 1 holds and the series sigma y n 1 to infinity converges. This is given. Okay. So, by definition of the convergence, a series is said to be convergent if and only if it is Cauchy. So, for a given epsilon greater than 0. So, for given epsilon greater than 0, there exists a positive integer, say capital M, which will depend on epsilon, such that for all m n, for all m which is greater than say n, n greater than equal to m epsilon. Of course, all m n greater than equal to m epsilon, I am choosing m to be larger than n. For all m n greater than equal to m, the condition that y n plus 1, y n plus 2 up to say y m is less than epsilon. Because basically this condition is what? This is nothing but the S m minus S n, where S m is the sigma by I is 1 to m. So, basically this is a Cauchy convergence criteria. So, a series, because it is given to be convergent. So, by means of the Cauchy convergence criteria, for any epsilon one can identify a positive integer, so that this result holds. Okay. Now, let us choose m to be greater than the maximum value of this k, for which this result is true, this inequality is valid, as well as the capital M, which we have already got it because of this convergence. So, if I choose m to be greater than this, then in that case the result, this thing, because y x n is less than or equal to y n. So, this part will give that x n plus 1 y n, x n plus 2, etcetera. This will imply that x n plus 1, x n plus 2 and so on up to say x m. This will remain less than by n plus 1, by n plus 2, y m, because x n is less, because m is greater than the number. So, it satisfies both the conditions, okay. And then this will be less than epsilon. This is true for all m greater than the maximum of k n d, and this is greater than 0, because all terms are positive. So, it will be greater than or at the most equal to 0. So, what this shows? This shows that this sequence S dash m minus S dash n, this remains less than epsilon for all m n n greater than equal to capital N, capital say k, maximum of k n epsilon. This is some integer, okay, k n epsilon. And where S dash m is what? S dash m stands for sigma x I is 1 to m. So, this shows the sequence x S dash n is a Cauchy sequence, therefore, it is convergent. So, this implies the series sigma x n 1 to infinity is convergent. Okay. So, the proof is very simple. The statement B follows from the first. It follows from what the we says the series diverges, then sigma b n diverges. Suppose the series given sigma x n to be a divergent series, and let this series sigma by n converges, but the relation 1 also holds. So, it means if a series by n is convergent, then according to the part A, x n must be convergent, sigma x n must be convergent, but it contradicts the result given thing, because the given is sigma x n is divergent. Therefore, a contradiction is because of our assumption this series converges. So, wrong. So, B follows from A immediately, okay. Nothing to prove here is, okay. Now, another test is or let us first take the test, then another test is which we call it as a limit comparison test. In fact, this is the modified version of this. Here, because it is very difficult to get this identity, which is valid for all n all after a certain stage. It is very difficult for a sequence x n and by n two arbitrary sequence are there. So, it is not possible always to get such an inequality. Therefore, this test comparison may not be very much helpful unless you know this inequality. So, what is a we have slightly it is modified and a simpler form is given which is known as the limit comparison test. The test says suppose x which is x n and y which is y n are strictly positive sequences of real numbers. And suppose the limit of this x n divided by y n over n when n tends to infinity exists. Suppose this limit exists, say is equal to r, this limit exists. Then what he says is if r is different from 0, means when the limit of x n over y n is different from 0, then the series sigma x n 1 to infinity is convergent if and only if sigma y n is convergent. It means the behavior of the series sigma y n and sigma x n are parallel, that if this limit x n over y n exists and different from 0, then both the series will have the same nature. If this series is convergent, this has to be convergent. Okay? And second part is if r is equal to 0. Of course, the divergence part here is not mentioned. Divergence we cannot say if it is one is diverging, other will also be divergent. But obviously, if we have this sort earlier relation, that also gives a result for a divergence of the series. But here we can only take the claim about the convergent part of it, that is, so far the convergence is concerned, both these series will have the same nature, same means convergent. Then and if r is 0 and if sigma y n is convergent, then sigma x n 1 to infinity is convergent. So, there is certain limitation in this. Limitation is that we are unable to test the divergence part. We cannot claim anything about the divergence, but obviously, for the convergent which we are interested more to judge the convergent with the help of the given series. Okay. So, let us see the proof of this. Now, what is proof is given the limit x n over y n as n tends to infinity is say r, which is different from 0 of course, r. Now, once the limit is given, then for any epsilon greater than 0, by definition what happened? By definition, this mode of x n over by n minus r, this will go to 0 as n is sufficiently large, or for a epsilon greater than 0, that is for a given epsilon, that is for given epsilon say equal to r, I am taking r by 2 greater than 0, there exists a integer, a positive integer say k, such that x n over y n, this will lie between what two bond r minus epsilon r plus epsilon r. So, here the r minus epsilon means r by 2, and then here is also r plus epsilon r by 2, and which is obviously less than 2 r. This will be less than or equal to 2 r. This hardly matters. Even this 3 by 2 will work. Okay. So, we get the 3 by 2, or this is equal to 3 by 2 r. Okay. 3 by 2 r into y. Now, if we like this, and this is true for all n greater than equal to k, is it not? This is true for all n greater than equal to k. So, this happens. Now, from here can we say that r by 2 into y n is less than equal to x n, which is less than equal to 3 by 2 r into y n. Okay. Now, apply the comparison test, and this is true for n greater than equal to k, because the by-n's are positive. Therefore, when we are multiplying this, it is not going to change the inequality as by-n's are greater than or equal to 0. Of course, greater than 0, otherwise this will equal to 0 will help problem. So, by-n is greater than 0. Now, apply the comparison test. So, by comparison test, we can get comparison test this is comparison O, and here also it is O, not I O, comparison test. Okay. So, by comparison test we can say the result A follows, the part A follows. Okay. That is what. Now, case second is part B. If r is 0, r is 0 means that is limit of this x n over by n as n tends to infinity is 0. Now, since x n and by n both are positive, non negative, so ratio cannot be negative. So, clearly from here it implies that x n over by n will always be greater than or equal to 0. In fact, it is strictly greater than 0, because they are non negative terms, strictly positive sequences of real numbers, strictly positive sequence of none is 0 even. So, x n over by n will be strictly greater than 0. Now, since the limiting value is 0, it means the terms keep on decreasing and decreases to 0. So, after a certain stage, this ratio will remain less than 1. So, once it is less than 1, so you can say this is less than equal to 1 for n greater than equal to k. This is true, because limit is 0 means it keeps on decreasing and decreases to 0. So, after a certain stage, the ratio will remain less than or equal to 1, and it is always greater than 0. So, now what happens? If we apply this, if suppose sigma by n is convergent. So, from here you multiply by n. So, this implies that x n x 0 is less than x n less than equal to y n. So, if sigma by n convergent, sigma x n will converge. So, part B follows. Clear? So, this is the two results which will help in getting the nature of this series, whether it is convergent or not. Only what we have to do, we have to suitably identify y n, okay, and then inequality or maybe the limit problem. Limit, so I advise that limit is a much better way of judging the convergence of the series. So, how to identify y n, so that limit of x n over y n will exist, and then nature of the y n will decide the nature of the x n. Okay, let us see the few examples which will help in getting this thing clear. Suppose I wanted to test the convergence of this series sigma n is 1 to infinity 1 over n square plus n. Now, when we say the convergence of the series does not mean that we are only we have to test only the convergence part. Convergence of the series means we have to see whether this series is a convergent series or divergent, but the way of writing is test the convergence means it includes both, whether the series is convergent or diverging. Okay. So, let us see, this is the sequence of non-negative real numbers, strictly of course positive, because n is 1 to infinity. Therefore, we can apply the ratio comparison limit test, but what comparison limit test says, there must be the sequence x n and by n. This sequence, if we want to test this series sigma n, you have to identify by n in such a way, so that the limit of this exists. In order to identify this, so here x n is giving to be 1 over n square plus n. Now, normally when we say the y n to be identified, we normally use this result sigma, we know sigma 1 by n to the power p when n is 1 to infinity. This is converges if p is strictly greater than 1 and diverges if p is strictly less than or equal to 1. So, basically the y n should be chosen in such a way, so that it will fall in one of the in this category. So, here what the trick is, let us take the here term n, anything common here outside, any n square if we take outside common, from the denominator take the largest power of n say outside, then what happens, if we choose by n to be 1 by n square, then when you are choosing n square outside, this becomes 1 over 1 plus 1 by n. So, limit of this x n over y n will exist. So, clearly limit of x n over y n when n tends to infinity is nothing but what? This is equal to n square over n square plus n, limit as n tends to infinity, divide by n square. So, 1 plus 1 by n and limit as n tends to infinity, and this limit is 1, which is different from 0. So, what we see here, that if x n and by n both are the strictly positive real sequence of real numbers, such that limit of x n over y n exists, which is different from 0. Therefore, this series is convergent if and only if this series is convergent, but this series is of the form sigma 1 upon n to the power p, where p is greater than 1. So, series converges. So, this implies that sigma 1 over n square plus n is convergent if and only if sigma 1 by n square is convergent, which is true, because of this. Therefore, answer is the series will be convergent. So, answer is the series 1 to infinity 1 over n square plus n is convergent. Okay. Now, similarly, if you go for the another example, say let us take this example, sigma test the series sigma 1 over under root n plus 1 to infinity. Again, this is a sequence of non-negative real numbers, strictly positive real numbers. So, to test this, we will apply the limit comparison test. So, let us take here, choose x n, here is 1 over root n plus 1. Then by n you take it the term which is highest power here is highest power here. So, highest power is 1, there is no problem, n the higher when you take outside, it is becomes 1 by root n. So, if I take this and the limit of x n over by n, when we choose the limit will come out to be 1, which is different from 0. You just see, take root n and divide by. It means the nature of these two series are identical, but the series sigma 1 by root n 1 to infinity, this is of the form sigma n to the power 1 upon n to the power p, where p is less than 1. So, diverges. Therefore, the series sigma 1 by under root n plus 1 will also diverge, and that is the answer. Okay. So, we can get it this way. So, main idea is that you have to pick up the suitably the terms by n, so that we can compare it with our given sequence given series x n, the terms of the series x n, and hence the one can identify the nature. Now, this is the one which we have a very important these tests are very interesting important, because it gives immediately the series nature of the series without going for the sum, because sometimes we are not interested in getting exactly the sum of the series or the limit of the sequence of partial sum, because it will not help us. We are not interested in finding the sum of the series. We are interested only finding the series whether it is convergent or divergent, and for this these tests are very much helpful.